harder. Thank you. All right. Let's see, there's nobody zooming in. So we'll take off with chapter 10, acids, bases, and salts. All right, we have a number of topics to cover, but the concept of acid and bases is really simple. Has anybody been introduced to that before, like in biology class or anatomy and physiology? No? Okay. Let's see. Do I have something for Seeger? No. Okay. Well, let's jump on our horses and ride off in every direction. The concept of acids versus bases was introduced in a quantitative sense by a Swede, Arrhenius. And the Arrhenius concept of acids and bases has to do with what's in the molecule when it goes into solution. And he was working with aqueous solutions. So anything, I'll use the a generic acid. Now always has, and we've learned this, of course, from nomenclature. Acids always start with a hydrogen, at least one, maybe two, maybe three, and then the rest of the molecule. And the reason we put these hydrogens out here is because those are the ones that can break loose from the molecule into solution. All right, so what they do is they release this proton and the electron stays behind. That gives the whatever is left behind a negative charge. Okay, this is the simplest expression of an acid dissociation in water. And in fact, we call it ionization because this bond is covalent. So we actually have to break that bond, a covalent bond, to give us this ion. Okay, that's Arrhenius concept of an acid. The Arrhenius concept of a base has some molecule and it's bound to a hydroxyl in the molecule. And when it breaks loose, the hydroxyl keeps the electron and what's left over has the positive charge. Now this is known as, ionization. I think I've got a slide on this too, but I thought I'd put it in here, stream of consciousness. And this is dissociation. This bond here is ionic. That one's covalent, according to Arrhenius. So this works for over 90% of acids and bases. And you're given a couple of examples there, nitric acid and sodium hydroxide, for example, acid base. But we could have, let's see, we could have something like that, sulfuric acid. Oh, and by the way, right, what do we say about acids and bases? You don't use the naming convention unless they're in solution. So this would have to be an aqueous solution, and it would produce one proton and then what's left over, right? And then we could take this one and do it again. Okay. So that's what would happen with a diprotic acid. All right. So here's the slide I was talking about. Ionization requires that for acids, requires that a covalent bond is broken. Now this covalent bond is not as strong as any other hydrogens. If you've got a molecule with other hydrogens in it, and they're in this part of the molecule, they're much more strongly bound. They do not ionize. For instance, acetic acid. Right? There's your acetate part of the molecule, the acetate polyatomic ion. These hydrogens are bound very strongly. They do not ionize, but this one hydrogen does ionize. That's why sometimes you'll see, I'll write it this way, or you may see it this way. We have that group, and then we have this carbon, and then we have that oxygen, and then we have this one like that. This is the hydrogen that is ionized. And those other hydrogens are bound to that carbon very strongly. So that's the only one that cuts loose. And then dissociation is based upon the concept that this is an ionic compound. So it's an association of a cation and a polyatomic anion. That's your author's idea of explanation. So which of the following describes an acid and a base in the Arrhenius universe? That one right there. So notice that when Arrhenius defines an acid, he says the proton must be part of the molecule. And when he defines a base, the hydroxyl must be part of the molecule. And there are various tests that were developed to distinguish between acids and bases. One of those is a change in color for like litmus paper. All right, does everybody use litmus paper? All right. If it turns blue, it's base. If it turns red, it's acid. Or let's see, we've used phenolphthalein in this class, have we? Yeah. So if it's acid, it's clear, and if it's a base, it turns pink. So those indicators tell you what type of solution you have, whether it's acidic or basic. Now the problem is we get a basic solution when we dissolve ammonia gas in water. It produces a basic solution. There are no hydroxyls in that one. So how do you explain that? Well, it's like any theory, right? There are three ways, actually four, but three ways you can deal with a theory that falls short. The Arrhenius theory for acids and bases will not accommodate this base. So what do? Well, you either modify it, right? Throw it out and start over, or restrict its application. Well, what we did was we proposed actually a different concept for acids and bases. And that was proposed by Lowry and independently by Bronsted in the early 20th century. So since they both published and proposed their ideas at roughly the same time, we give them both credit. Bronsted, Lowry, sometimes it's Lowry, Bronsted, acids and bases. Okay. The concept that we have developed with Bronsted and Lowry, let's just erase all this and start over. That's going to be too much work. Let me try this. That's better. Let's see, I'll put it out the way they did it. Bronsted and Lowry. I always want to put an E in there. So the Bronsted-Lowry concept is based upon just what happens with the proton. Now, the proton doesn't have to be part of the acid to be part of the reaction that gives you an acid and base. Now, if it's like this, right? And we're calling that an acid, that means this must donate the proton to something else. So if we put it in water, it actually reacts with water. And it donates that proton to the water molecule. Anytime a proton is created in solution, it's always transferred to something else. Protons never exist independently, just free floating around in the water. It doesn't happen. So this proton then would be donated to that water molecule. What's left over? Well, like before, you have that anion left over from the acid. And then what happens to the other proton? It's added to the water molecule with a positive charge. Okay. So this is known as the hydronium ion. It is a polyatomic ion. It exists with that positive charge distributed over the entire group. And all of those hydrogens are covalently bound to the oxygen. Let's see, I got something to return to you guys, right? Bailey? You guys were here last week, so you got everything except next week's lab. You grab it when you have a chance. All right. So that's the concept behind the acid, is a proton donor. A base is a proton acceptor. So if we say, let's see. Well, let's use ammonia, right? Ammonia is a good example of the species that cause the problem. So what happens if we have ammonia in here? If it's going to be a proton acceptor, where does it get its proton? Well, if you dissolve ammonia gas in water, there's only one place that the proton can come from. It has to come from water. Right? So if we dissolve it in water and we take a proton here, this is the proton acceptor, right? Proton goes from there to there. Now we have the polyatomic species, the ammonium ion. Okay? And these are all in aqueous solution. I just didn't draw aqueous in there. What's left over? Well, remember, water's like this. If you take a proton away from it and leave the negative behind, what do you got left over? You have a hydroxyl left over. Okay? So that's where the hydroxyl comes from. It doesn't come from the molecule itself. Okay, that's the essential difference between Arrhenius and Bronsted-Lowry acids and bases. This concept covers, whereas Arrhenius covered 90% of acids and bases, Bronsted and Lowry can cover 99.9% of acids and bases. Okay. All right. So, which of the following describes Bronsted-Lowry? It's that one right there. It's based upon proton or hydrogen. I say proton because what do you have with a hydrogen atom when you take the electron away? There's nothing left but a proton, right? For most of the isotopes, right? We'll leave deuterium and tritium out of the mix right now, but they're still in there. I just use proton for convenience. All right. So we've got a definition situation here. Let's use, well, we can use the one that they just presented, right? Hydrofluoric acid, HF. All right, let's make it complete. This is a pure liquid. And if we transfer that proton over, what do we have left over? We have the fluoride ion in solution and the hydronium ion in solution. This is the acid, right here. This becomes the base, right? Because it accepts the proton. So water is the base in this case. When we produce the product side, now this is capable of accepting a proton. So it's a base, but it's the conjugate base of that acid. So to distinguish them, excuse me, I can't write. Conjugate base of the acid. That makes this one the conjugate acid. Okay? Just so that when we say conjugate, we mean product. Okay? So the conjugate acid-base pair. All right, when we say conjugate acid-base pair, we mean the acid, here would be the acid, right? And then the conjugate base would be this molecule minus one proton only, right? Because each reaction happens in steps. Since we only have one proton, it only happens once. But if we had two, for instance, back to our sulfuric acid, there's the acid. What would we have left over as the conjugate base? Just take away one proton. There, that's the conjugate acid-base pair for the first ionization. The second ionization conjugate acid-base pair would be this. Oops. Like that. That. And what would be left over, right? That's a conjugate acid-base pair. This is a conjugate acid-base pair. And to answer that question, there they are. All right. Notice that if this is the base in this reaction, that makes this the acid. It's the proton donor. Water can be, depending on its environment, can either be a base or an acid. We call that amphiprotic or amphoteric, either one. Amphi is the Greek prefix that means both. So depending on how it's used or how it is reacts, it can either be an acid or a base. Now, water is not the only molecule that can do that. Right? If you have, anybody know, well, probably in the hills, we don't have too many big corn farmers. It takes a lot of land to make it economically feasible to use anhydrous ammonia for your nitrogen fertilizer. But in, say, Iowa, where they grow a lot of corn on the flat, it's more economic to deliver your nitrogen fertilizer to your plants in the form of anhydrous ammonia. Right? It's cheaper, more efficient, but it takes specialized equipment. We won't go through that right now. My point is, when you have ammonia and nothing else in there, I say anhydrous, that means no water. It's 100% ammonia. Then one ammonia molecule can react with the other ammonia molecule, and one is the acid and the other is the base. So ammonia can be amphoteric also. So this would give up, right? So that proton goes over here, it makes that negative, and we have this. So that would be a reaction that would occur for pure ammonia. So water is not the only amphiprotic or amphoteric. It can happen with other molecules. All right, naming convention, of course, monoprotic acids only have one proton or one hydrogen that's available for ionization, like hydrofluoric acid, nitric acid, okay, hydrochloric acid. They only have one hydrogen available. Right? Diprotic, they've got two hydrogens available, like sulfuric acid or sulfurous acid. If there are two or more, well, triprotics also. Triprotic acid, the only one I can think of offhand is phosphoric acid. And it would go through 3 steps to get all those protons off. But if it has two or more, we can also call it polyprotic. Okay. Now, the chemical definition for strong versus weak. Let's make some room here. When we say strong acid, the conventional wisdom or conventional understanding of strong versus weak is strong means it'll do damage. Weak means it won't do damage. But in chemistry, we've got a slightly different definition. A strong acid is 100% or almost 100% ionized acid. Hydrochloric acid fits that bill. When you put hydrochloric acid in water, it will dissociate, and there's a caveat here. I write it this way for convenience. I already told you that proton doesn't exist separately. So the actual reaction would be what? This one plus water yields this one plus the hydronium ion. That's the real chemistry. Oops, that's aqueous. This is the real chemistry. We write it this way sometimes for convenience. If you have to do any calculations or any type of reactions, this works just as well as that. But I just want you to realize that this is the real chemistry and this is convenience, kind of a shorthand version. But back to the topic. This reaction goes essentially all the way to the right. No returns. Goes all the way over here. Now you've got your hydronium ion and your chloride ions in solution. That's it. The first hydrogen ion from sulfuric acid does the same thing. Second hydrogen is another story. Let's see. What's another example? Nitric acid. Nitric will do the same thing. It's a strong acid, essentially 100% dissociation, ionization, excuse me, ionization. Hydrochloric, hydrobromic, hydriodic, those halogens produce strong acids. Other examples, nitric acid, chloric acid, perchloric acid, sulfuric acid. And like I said, sulfuric acid is strong for the first proton only. HF is not a strong acid. It's considered a weak acid. In chemical terms, and a weak acid only gives up a small percentage of its hydrogens to ionization. So HF as an example for a weak acid. Would be HF, I'm going to write this one correctly, aqueous plus water yields fluoride ion plus hydronium ion. Now, the way we write this to symbolize weak acid is it goes this way part of the way, but most of it goes like that, stays over there. You only get part of it over here. Now, it doesn't say anything about the corrosive nature of these acids. In the chemical terms, it just says, what is the extent of ionization? Okay. The concentration tells you whether it's corrosive or not. And OSHA and EPA standards are set for what constitutes corrosive acids and base solutions. All right. So this is your author's idea of an explanation. Strong acids go all the way to the right. Weak acids only part way. And we can use the same concept for bases. Strong bases completely dissociate from one to the other. So all the alkali metals and a couple of the alkaline earths, all the alkali metals, lithium, sodium, potassium, rubidium, cesium, all the alkali metals are strong, and calcium, strontium, and barium hydroxides are strong, but there's a caveat. All the alkali metals, let's see, strong base. So let's take lithium, for instance. Lithium hydroxide would go all the way to this one. Now, in this case, the hydroxides do exist as free floating, but they always associate with water molecules. They're not transferred to the water, they're hydrated. There's a distinction there. This is all the way to the right. And you can say the same thing about sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. When we get to the alkaline earths, calcium hydroxide, for instance, will completely dissociate like that. The caveat is that these compounds are only very slightly soluble in water. But whatever goes in solution completely dissociates. You see the distinction? For the alkaline metals, everything goes into solution and dissociates. But for the alkaline earths, whatever goes into solution dissociates, but only small amounts of it go into solution. They're actually considered insoluble. If you look at the table I gave you in a previous chapter, right, with the clear boxes and the grayed out boxes. If you look those up, you'll see that they're considered insoluble. But whatever goes into solution completely dissociates. So that makes them strong bases. But in order to get corrosive solution, you'd have to really boost the solubility up as high as you can. And that means you put a lot of this and have a lot of it sitting on the bottom of your beaker, saturate the solution. Plus, if you want to get more of it in solution, you heat it up. All right. So that's another example of chemical definition of strong versus weak. Weak bases. Let's see. Well, ammonia is a weak base, right? Ammonia dissolved in water only partially goes to the basic side. So we get most of it back over here, and that produces the ammonium ion and the hydroxyl ion. So in ammonia solutions, like you can buy on the on the grocer's shelf, ammonia, right, for cleaning purposes, or, well, yeah, Windex now is not pure ammonia anymore. It's a tertiary, quaternary ammonium compound, and safer. But you can still get ammonia in the bottles. In that bottle, the ammonia in that bottle is mostly here. Very little of it is over here. I think I calculated one time, 97% of it is over here. Okay, which of the following equations would be the correct presentation of strong acid when placed in water? That one, the big arrow to the right. Little arrow to the return. Actually, I wouldn't even put a little arrow to the return in there. Okay. Now, here it is. We've got those forward facing arrows and the reverse facing arrows, implying that once you build up enough product, you start getting a return reaction. And that's characteristic of any chemical reaction. It goes both ways. But as far as the acid ionization goes, there's a constant value. We talked about this in a previous chapter, didn't we? Equilibrium. Yeah, okay. So the equilibrium concept for acids would be like this, right? And we're going to write it out correctly. Pure water, right? And then we have this left over, conjugate base of the acid, and then the hydronium ion, which is an aqueous solution. Okay. Remember how we write the equilibrium constant for this one? Concentration of products, product of those concentrations divided by the concentration of the reactants. So we would say this one, and this has a subscript of A referring to the acid dissociation. Or actually, it should be called acid ionization constant. So we would put the equilibrium concentration of the conjugate base and the equilibrium concentration of the hydronium ion divided by what's left over of the unionized acid. And notice we leave the water out because we don't put pure liquids or solids in our expression. Right? That's the correct expression for acid ionization. Equilibrium constant for an acid. Another way of expressing this is in terms of ratio of this value to that value, right? Percent dissociation. So percent dissociation is simply the concentration at equilibrium, the concentration of the conjugate base divided by the acid concentration times 100. Okay. Two ways to express the outcome of the reaction. The percent dissociation, actually, you probably saw this already coming. Ionization. It should be percent ionization for acids. The percent ionization is an expression of how strong the acid is, right? Because it ratios this part to that part. So if this is very high, that means it's mostly over here. So a higher percent ionization indicates strong versus weak in terms of the acid strength. Now, and the acid strength also increases with a Ka. If we look at it one versus the other, if this Ka is very large, then we're saying that it's mostly product. Right? It's mostly ionization, the ionized product. So either way expresses the strength of an acid. Now we could hammer that one for the rest of the class session, but I only do that in the general chemistry class. Base ionization constant. So if we have a base, and yes, we put it in solution, and react it with water. Then we transfer hydrogen from the water over to the base. It's the proton acceptor. And we have leftover hydroxyl. Then we can write Kb for this one. Let's see, they use a small b, don't they? Okay. Be consistent. Would be if this is the base, what's this? The conjugate acid. Now it has a proton it can donate. That makes it an acid. And then the hydroxyl divided by, this is liquid, divided by a B. Okay. That's the equilibrium constant for the base. Now, we could write this for a strong base, but it wouldn't mean much, right? Because it'd be actually infinity. This would be so small, this would be so large. It would essentially be like that. Same thing for the acid. All right. So that's your introduction to acids and bases. Now, what's actually more interesting is when you get acids and bases together. What do they do? So we're introducing the concept, the chemical definition for salt. We got an acid and base. A salt is one of the products of a reaction of an acid and a base. And in this case, I'm not talking about water. I'm talking about what would react with water if you put it in solution. So if we have an acid, and we're going to restrict our base for the time being to an Arrhenius base. It's easier to track that way. And then when it reacts, this is like a double displacement reaction, right? This one swaps places with that one. So if this hydrogen comes over here to that hydroxyl, what do you get? Water, right? Okay, what's left over? Well, you have the cation first and the anion second. And they could be water soluble, some of them are not. They might precipitate out. But this being the acid is the proton donor, this being the base is the proton acceptor, or it could be an Arrhenius base, the hydroxyl dissociation, and produces water and a salt. That's the chemical definition of a salt, the product of an acid-base reaction. There you go. Okay. This is also known as a neutralization reaction. And as written, the stoichiometry in this case says 1 mole of that plus 1 mole of that disappears and produces a mole of that and a mole of this. Now, the stoichiometry can be different depending on the acid and the base. But if you have exactly the right amount of this one and exactly the right amount of that one, to combine them both, they disappear and produce these. That's neutralization. Well, actually, you can neutralize up to a point and only partially neutralize. I should clarify. Our example there, hydrochloric acid and potassium hydroxide. Those are both strong, right? Strong acid, strong base. So we know that they are in solution as hydronium ions chloride ions, potassium ion, and hydroxide ions. And the hydroxides react with the hydroniums and produce water. Plus the salt. The second reaction, where we have sulfuric acid and potassium hydroxide, you need 2 moles of potassium hydroxide to be stoichiometrically equivalent to 1 mole of sulfuric acid, simply because sulfuric acid has the potential to ionize 2 protons. Now, the first proton is strong. It comes off. I mean, you just have to look at it crooked and it'll come off. The second one has to be coaxed away. And that's what the strong base is for. Strong base will draw that hydrogen off of the HSO4 minus ion, pull it off, and you're left with sulfate. And sulfate plus potassium gives you potassium sulfate. Now the question is potassium sulfate soluble? And if you look at your chart, follow the cations and anions, yeah, it's soluble. So in solution, you would have 2 moles of potassium, 1 mole of sulfate ion, and water. But you still have overall reaction. Potassium sulfate is the salt. And this would be a neutralization reaction. Acid, base, salt, and water. Most of the reactions that we'd be interested in are the Arrhenius types of acids and bases. They're the most common anyway. But we're always mindful of the possibility of using Bronsted-Lowry types in order to produce the reaction we're interested in. All right. So here's what would happen if you have, the net reaction. So if we have, let's use a real one. Let's say we have a strong acid and a strong base, right? And it produces sodium chloride. We know that's soluble. That's your salt and water. Okay? In solution, this is actually going to be, and I'm using the abbreviated form. We know that's a hydronium. In solution, it would look like that. And this as reactants. And then when they get together and react, they produce this soluble salt. Plus water. Okay? That's the complete ionic equation. Did we do that in this class? Molecular equation, complete ionic and net ionic. Maybe we didn't do that. Okay. Consider this an illustration. Okay, but that's what it would look like in solution. Actually, you have the individual ions and you have this as products. Okay, notice that you've got sodium ions on both sides. And remember, when you put these together, they're all in that same beaker. All this stuff is happening in that same beaker. So these sodium ions show up over here. That means for the net understanding of the equation, they can cancel out. Same thing for the chlorides, right? So what do you have left over? We can't cancel the hydrogens or the hydroxides or the water. So what we have is the net ionic equation for an acid-base reaction is that. Which is nice. I mean, if you want to have an acid-base reaction and say you don't have sodium hydroxide on your shelf. Say you have potassium hydroxide. Potassium hydroxide would work just as well because it's a strong base too. Or you don't have hydrochloric acid, but you have nitric acid. It's a strong acid. So yeah, the nitrate was on this side and it's on this side, cancels out, leaves you with that. So you can do the same reaction with different compounds if you're looking to construct an acid-base reaction. And that's what we see there. The hydronium there is like this. Then the hydroxyls produces water. Okay. So a neutralization reaction produces water and a salt. Okay. So let me erase this so make room. We mentioned the amphoteric nature of water in terms of water being able to serve as an acid or a base. But if you have pure water, water molecules are still going to react with one another, just like I showed you with ammonia. You have one water molecule here, another water molecule here, and one of them is an acid and the other is a base. Take your pick. We'll call this one the acid and this one's the base, which means that was the proton donor, right? And it leaves you this. It lost a proton. And this one picked the proton up. That's known as self-ionization. Sometimes it's written this way, just for convenience. And for calculation purposes, this is the one that's usually used for calculating the K value. So the K value for this one, and it has a subscript of W. And that says this K is only valid for that reaction. So we would put what? Hydrogen ions or hydroniums, hydroxyls. What's in the denominator? Nothing, right? That's pure water. So the Kw for water is simply the hydrogen ions or the hydroniums times the hydroxyls concentrations at equilibrium. Okay. And at, I think it's measured at 24 degrees Celsius. The value in here would be 10 to the minus 7 molar. Yeah. And that means since they come from the same water molecule, the hydroxyls have to be exactly the same concentration, don't they? Right? Because we're just splitting that molecule. So if we get that concentration for the hydrogen ions and that concentration for the hydroxyls has to be. So when you multiply those together, you get 10 to the minus 14. That's equal to Kw at that temperature. Okay. I'll take you back to that one in a few minutes when we talk about pH. Okay. Let's see, self-ionization. There's the ion product, right? They put the coefficient in there too, but since it's 1, I just left the 1 out. And another factor is that when you have reactions, acid-base reactions in solution, this reaction is always happening. No matter what else you put in solution, this is always there. So if we put a strong acid in there, this is still going to happen, only if you have the concentration of the acid high enough, it won't matter, right? Because the acid is so strong, it sort of overwhelms this part. So you have to decide when you're putting an acid in solution, is it strong? Is it weak? How weak is it? To decide which reaction is the dominant one. Right? Sometimes you've got the concentration of a strong acid so diluted that it doesn't make any difference. And this is the governing reaction. All right. So when we have a neutral solution, we're saying neutrality is where the concentration of hydrogen ions equals the concentration of hydroxyl ions. That would be the case here, right? Pure water is an example of a neutral solution, right? And it doesn't matter what the concentrations are as long as they're equal. If it's pure water, of course, they're going to be 10 to the minus 7 molar. But if it's some other type of solution where you have, say, an acid-base reaction, you may have, this is be a higher value, like 10 to the minus 3. Well, that would have to be 10 to the minus 3 also. If the an acidic solution is one where the concentration of hydrogen ions is greater than concentration of hydroxyl. So if we took pure water and added some hydrochloric acid to it, maybe 10th molar would be a good choice, then it would definitely be acidic. We would have a higher hydrogen ion concentration than hydroxyl. And if we put sodium hydroxide in there instead, then we would have, then we would have hydroxyl ion concentrations greater than hydrogen ion concentrations. And again, these are hydroniums. That's what that description is trying to show. The misleading part is that as you go up on the y-axis, concentrations get smaller, right? It goes 10 to the minus 1, minus 2, minus 3, minus 4. It's getting smaller as you go up. So it kind of messes with your mind if you don't pay attention. Because it looks like the hydrogen ions are lower than the hydroxyls in the acidic solution, but that's not the case. It's the other way around. Okay, so I put that on the board already. All right, so let's see if we can use what we've learned to do a calculation. Okay. Calculate the hydrogen ion or the hydronium ion and or hydroxyl ion concentration as required for each of the following solutions, and state whether the solution is neutral, acidic, or basic. Okay. If the solution is 1 times 10 to the minus 4 hydroxyl, 1 times 10 to the minus 4 hydroxyl, yeah, hydroxyl, I would do like that. Then what would the concentration of hydrogen ions be? We know that this times this equals 10 to the minus 14, correct? So this would be 10 to the minus 4, and that would be unknown. All right, so if we solve for the hydrogen ion concentration, then it'd be 10 to the minus 14 divided by 10 to the minus 4. And what would that give you? If we bring this one into the numerator, it becomes positive power, right? And then you just add the exponents. Plus 4 and minus 14 would be 10 to the minus 10 molar for hydrogen ions. That is basic. Because this one is much greater than that one. Or another way of looking at it, in neutral water, it's 10 to the minus 7. This is a lot less than 10 to the minus 7. This is a lot greater than 10 to the minus 7, which also means it's basic. So let's see, did I put an animation in this one? Yeah, here we go. There we go, and there we go. 10 to the minus 10. And we left out the molar part. There we go, basic. How about 2 molar hydronium ion or hydrogen ions? Either one. Oops, I shouldn't have erased that because I'm going to need it again. So if again, we have this expression, 10 to the minus 14, then, and we have 2 molar here, right? So this is going to be what? 10 to the minus 14 divided by 2. So that's a half, right? A half times 10 to the minus 14. Or 0.5 times 10 to the minus 14. And see, we move it over here like this. That makes this one times 10 to the minus 15. That's definitely very low concentration of hydroxyl, very high concentration of hydrogen. That's an acidic solution, no doubt about it. There we go. Well, I went to a lot of extra trouble. This is much, much greater than 10 to the minus 7. So that's definitely acidic. All right. So there's your definition. And now we're going to look at pH. Anybody been introduced to the concept of pH? Okay. pH was proposed by, I think, is he Danish or Swedish? Danish. Sorensen. Well, not too long after Bronsted and Lowry proposed their definitions, Sorensen was working with solutions of certain hydrogen ion concentration, hydroxyl ion concentration, and it was very cumbersome for low concentrations to simply use scientific notation for those values. He wanted something that was a little more convenient. So he decided, well, look, if I just take the log of the hydrogen ion concentration, I can get a compact number, right? So he said, all right, if I take the log of the hydrogen ion concentration, and let's just say it's neutral, 10 to the minus 7. So the log base 10, right? This is common logarithms. Everybody remember logarithms from math class? Okay. What does that mean when we say that? The log of this number is the power of that number that is this number. So that would be 10 to the, actually not 10, be minus 7, wouldn't it? Minus 7 is the log of that number. Okay? Well, he said, I don't want negative numbers. Right? That's almost as bad as scientific notation. So he said, all right, I'll just put a negative over here. Now it makes it positive. So the negative log of the hydrogen ion concentration is pH. Small p, capital H. Not capital P, capital H, not capital P, small h. Small p, capital H is pH. And it became very useful. It was quickly adopted by anybody, any scientist working with acids and bases latched on to that one. In fact, the story, this is just the beginning of the story. Now, for Sorensen's purposes and for most scientists' purposes, the pH range that they're going to be interested in is not even down to 0. It's usually between 1 and, say, 13 or 12. But it's just a mathematical expression, right? Negative log equals pH. So you can do the negative log of anything. In this case, it's a negative log of the hydrogen ion concentration, but you can do the negative log of anything and call it P something if we use that naming convention. So if we have hydrogen ion concentrations of 10 to the minus 4, 10 to the minus 4. I left the 1 out because what? Well, let's do it that way. At least this first time. Let's say 1 times 10 to the minus 4, and it has to be molar. Okay? And we're going to take the negative log of that. Okay? So what's the logarithm of a product? Remember that? It would be the negative log of 1 plus the negative log of 10 to the minus 4. Right? That's the way logarithms work. Well, what power of 10 gives you 1? 0. Right? 10 to the 0 is 1. So that's why I left the 1 out the first time I wrote it. How about this one, though? 10 to what power is 10 to the minus 4? It's minus 4 times that one. Right? So that's the pH of 1 times 10 to the minus 4. There you go. Oh, significant figures. This is the way logarithms work. If, let's see. For significant figures, you do have to know the coefficient in order to determine the significant figures. So the significant figures of this number are how many? 2, right? 2 sig figs. When we convert it into pH, then those significant figures are translated into decimal points for your pH. So it would actually be 2 decimal points. Okay. That would be the pH. So if we go backwards, if you worked backwards from here to there, then you would have 2 decimal points. That's how many significant figures you would have in the hydrogen ion concentration. And you can work backwards. It's called anti-log. We'll probably do one of those in a few minutes. Okay. Let's make some room. And the only way you're going to get comfortable with these, if you're not already comfortable, is to take that review document and work these problems. Work all of them if you can. How about 0.040 molar hydroxide? 0.040 molar hydroxide. Well, the pH is based upon hydrogen ion concentration. So we need to multiply this times that, which is equal to 1 times 10 to the minus 14, right? Okay. So the hydrogen ion concentration then would be 1 times 10 to the minus 14. And let's convert that one. So that'd be 1, 2 to the right times 10 to the minus what? 2. Okay. So we can do these separately. 1/4, 1.0, about 4.0, which is what? 0.25 times 10 to the what? Minus 12, correct? Okay, so that's 2.5 times 10 to the minus 13. That's the hydrogen ion concentration. So we take the negative log of that value. And that's equal to pH. I need my calculator for that one. And every calculator has a log key on it. Well, every scientific calculator does. Let's see. 2.5, and then my exponent is minus 13. Oops. That's not going to come out right. There we go. Now I'm going to take the log of it, hit my log key, but it gives me a negative sign. I got to get rid of that negative sign. So I just change the sign. All right. We've got 2 significant figures. So I get 2 decimal points. That's 12.60 pH. Okay. Let's see if it agrees with my animation. There we go. Okay. That's the longhand way of doing that calculation. I hope, I haven't taken a peek at my slides to see. The pH of a solution is 5.85. What's the hydrogen ion concentration? Okay, now we're going to go backwards. So let's make room. All right, if pH is equal to 5.85, then that is equal to the negative log of the hydrogen ion concentration, right? Okay. In order to solve for that one, we have to know how logarithms work. If you've got a negative here, you can't have a negative there when you take the antilog. You got to get rid of that negative, right? But it has to still be equal. So if we take that negative, it goes on this side. 0.85 equals the log of hydrogen ion concentration. There you go. Now we can move ahead. If this is base 10, then that is the power of 10 that equals this. That's what antilog is. All right, so we say 10 to the minus 5.85 is equal to hydrogen ion concentration. There you go. Now all we have to do is punch it into the calculator. 5.85, change the sign, and then do antilog. So what's antilog on your calculator? Sometimes it says antilog, but very often it says 10 to the x. And it'll be a function of log. In my case, I hit the function key, and right above it is 10 to the x. So this would be like that. And that's 1.4, let's see, 2 decimal places. So that gives me 2 significant figures times 10 to the minus 6 molar. Okay? There we go. All right, so if we're working with only pHs, and say you have a pH meter, everybody know what a pH meter is? It's an electronic device with a probe that you stick in your solution, and if it's properly calibrated, the meter will read the pH of that solution. And it skips the part with about hydrogen ion concentration. It just goes straight to the pH. So if that's our situation and we're not interested in the intermediate scientific notation, then we need to understand what our pH means. So on a continuum, right, in the middle is pH 7. That's neutral. If your pH meter says 7, your solution is neutral. In other words, the hydrogen ion concentration, hydroxyl ion concentration are exactly equal. And more than likely, they're 10 to the minus 7th molar. If we go bigger than that, this side, right, remember, that's basic. So we can go up to, say, 14. We're going to stretch it. This is basic. If we go less than that, down to, say, well, 0, then this is acidic. Why? Because it's not only logarithmic, but we introduce that negative sign. And the negative sign causes it to go to flip. So the bigger the pH, the more basic. Smaller the pH, the more acidic. All right. And this scale just gives you some pHs of some common vegetables. Well, egg's not a vegetable. Egg whites are in the neighborhood of 7. Butter is slightly acidic. And you get more acidic as you go toward limes, right? What causes citrus fruits to be acidic? Citric acid. Citric acid, primarily. There's some ascorbic acid in there, vitamin C. Apples are a little bit acidic. Now, the ones that you bite into and they're a little bit tart, sweet tarts, those are more acidic than the ones that are kind of mushy. Like, let's see, what's that red apple that's old cultivar? I can't even remember it because I never buy them anymore. They're not too common. Let's see, strawberries can be a little acidic, right? Tomatoes, definitely. All right. Does anybody know the pH of your blood plasma? Normal pH range. It's very narrow. 7.35 to 7.45. Extremely narrow range. And if it gets above or below that, you don't feel so good. Now, if you're diabetic, you're likely to go acidic. They call it ketoacidosis. And there's a complex metabolism that's involved in there. We won't go into that. All right. So which of the following is the correct mathematical expression for pH? Right there. All right. Now, I mentioned earlier, I probably blew by you too fast. pH is a mathematical expression, negative log of hydrogen ion concentration. You can do negative log of anything. So if we say negative log of the hydroxyl ion concentration, what would that be? POH. Okay. Yeah, it's just math. Say we had a Ka, right? That would be some value. We could do the negative log of that. What would that be? pKa. Okay. Or we could do the same thing with that special one for water. Negative log of that one. That would be pKw. Now we know what that one is because this is supposed to be 10 to the minus 14. So pKw at 24 degrees Celsius would be 14, right? Okay. Here we go. All right. We know from our previous expression that Kw is equal to hydrogen ion concentration times hydroxyl ion concentration is equal to 10 to the minus 14. Okay. So if we do the same thing to both sides of the equal sign, both sides, then we haven't changed it, right? That's allowable in math. So let's take the negative log of the whole equation. Just take negative log of this, negative log of that, and the negative log of that. Okay? So what do we get? Well, we get pKw over here. We get pH here. And when you take the log of a product, what do you have to do to it? Addition, right? It's not a product anymore. When you take the negative log of that, it's pH plus POH. And then this one we just did is 14. So there's another equation that's very useful. Let's see. I think this one goes further. There we go. So this is a quicker way. Remember that the example we had earlier where we wanted to know the pH, but we were given the hydroxyl ion concentration. We had to calculate the hydrogen ion concentration, then do the pH. Well, in this case, we could take that hydroxyl, calculate its POH, stick it in this equation and calculate the pH. That saves us a step. So what's the pKa for HF? Okay, so we're going to do hydrofluoric acid. If the Ka for this acid is 6.8 times 10 to the minus 4, what does that mean? Let's see. Let's make some room over here. What are we doing on time? 10:30. Okay. If the if it's HF in aqueous solution, and we're using the simplified version. Oops. 1 hydrogen plus fluorine. Okay. Then the Ka for this is going to be the equilibrium concentration of hydrogen ions, fluoride ions, and then HF down here. And that's equal to 6.8 times 10 to the minus 4. Okay. This is a weak acid, right? Because that's a very small value, which means this has to be very small. That means there's not much of it over here. Most of it's over there. Okay. So that tells you it's a weak acid. It's much, much less than 1. So we want to calculate the pKa, right? So the pKa is equal to the negative log of this value, 6.8 times 10 to the minus 4. All we have to do is plug that into our calculator. Minus 4, take the log of it, and change the sign. And let's see, we've got 2 significant figures. So we can have 3.17. 2 decimal points is our pKa, 3.17. Let's see, did I animate it? Yeah. So what does that tell me? That tells me if I know the pKa, I can tell just how acidic this acid is, right? If the value for if the pKa is very small, it's like pH. The smaller the value, the more acidic the molecule. So if it came out for some other molecule, it was like 5, it would not be as acidic as hydrofluoric acid. Or it came out as 1, it would be more acidic than hydrofluoric acid. All right. pKa is another method of expressing the strength of acids. And there's the definition. If the Ka of a solution is 6.3 times 10 to the minus 4. Okay. Did I do that one right? Yeah, 6.8. If it's 6.3, what's the pKa? All right. So the pKa would simply be 6.3 times 10 to the minus 4. Take the log, change the sign. So that would be 3.20. And is the solution acidic or basic under standard conditions? What are standard conditions? Well, 25 degrees, which is pretty close to 24. 25 degrees C. Let's see, 1 molar concentration. So that's pretty concentrated. And if there are gases involved, it's 1 atmosphere pressure. So under standard conditions, I would expect it to be acidic with a 3.2 pKa. Okay. Okay, now we talked about salts and how we derive salts from an acid-base reaction. But suppose you put a salt into pure water. You've already got the salt, like sodium chloride, sodium nitrate, whatever else, ammonium phosphate, for instance. Put it in solution, right? What are you going to get? I mean, is the solution going to be neutral, acidic, or basic? That's good information to have. Well, first of all, we have to understand how the salt goes into solution. Right? It's a process of hydrolysis. In other words, the salt breaks up into individual ions if it's completely soluble. Right? If it's only partly soluble, then whatever ions go into solution are surrounded by water molecules. Right? And we looked at water molecules earlier, I'm pretty sure, as a polar molecule, right? With a dipole moment this way, which means this is slightly negative. And let's see, let's balance it. Positive ends over here. So the water molecules are going to associate with the ions of the dissociated to the hydrolyzed salt, so that this end of the molecule is going to be, associated with the cation, and this end is going to be associated with the anion of the salt. And they surround the cations and anions in a process called hydrolysis. Okay. Now, if you want to determine whether the solution is neutral, acid, or basic in qualitative terms, then all you need to know is what's the origin of each, the cation and the anion. Right? I'm going to give you the rule of thumb first and then the chemistry afterwards. The rule of thumb is if the salt is derived from a reaction of a strong base and a strong acid, your solution will be neutral. Okay? Come on. Here we go. If, on the other hand, your solution is derived from a strong acid, so a strong acid like hydrochloric acid would produce what? Chloride ions. And the base happened to be weak, like ammonia is a weak base. So ammonia is going to produce, let's see, it reacts with water and produces ammonium ions and hydroxyls. Then this cation associates with that anion. And the rule of thumb is if the anion is derived from a strong acid, then the solution of the strong acid and weak base will give you an acidic solution. Okay. Well, in this example, we have sodium hydroxide as the strong base. The weak acid is acetic acid. So that means it's going to be a basic solution. Okay. Now the chemistry behind this, that's the rule of thumb. The chemistry behind this is when you put these in solution, say you have sodium acetate, C2H3O2, and put it in solution, and you get sodium ions and acetate ions. Let's see. So don't get confused here. Let's remove that stuff right there. Now they're in solution. So what is there in there? What is in the solution for them to react with, if anything? Right? Sodium could react with water, right? Or it could react with hydroxyl ions from the dissociation of water molecules. Right? What is it going to do? Nothing, right? Because sodium is derived from sodium in this situation would be derived from this one. It produced that and that, and it's all the way to that side. What does that mean? That means when you have sodium ions in solution, it's not going to react with anything. It doesn't want to go back. It wants to stay over here like that. So the sodium ions are not going to react with water or hydroxyl ions, either one. But the acid that is associated with the acetate ion is a very weak acid. So when it dissociates, there's not much over here. C2H3O2 minus. Not much over there. So where does it want to be? It wants to be over here. When you put it in solution, then that ion is going to want protons from somewhere. And it's going to get them. So we're going to take this over here. You put it in solution as a consequence of this dissolution. That would react with water molecules and take a proton from that water. So water becomes the acid, donating to this conjugate base. What do you get from that? You get this, right? Plus that. A lot of it. Because it wants to be this side over here. That leaves behind hydroxyls. That gives you a basic solution. So the rule of thumb is salts derived from a strong base and a weak acid give you a basic solution, not because of the base, not because of the strong base, but because of the weak conjugate base, the strong conjugate base of a weak acid. I didn't mention that earlier. Let me give you that right now. When you dissociate a weak acid, it produces a conjugate base. Weak acids produce strong conjugate bases. In other words, they want protons from somewhere. Okay, that means they want to be back this way. And a strong acid produces a weak conjugate base. Once it gets to be the conjugate base, it wants to stay there. Okay. All right, that's the chemical definition, the explanation for the rule of thumb. Now, if you have both, if the salt is formed from a weak acid and a weak base, then it could produce any range. It could be acidic, neutral, or basic. It just depends on which one is the weak acid is a stronger acid than the weak base, or vice versa. We'll send it in both directions. And in this class, we really don't have the opportunity to give you more than just that definition. Could be either way. So I'm going to have to let it go at that. All right. Some salts hydrolyze when placed in water. The salt dissociates in water to produce hydronium ions, hydroxide ions, or both. When the salts of the strong acid and the strong base are placed in water, the resulting solution is neutral. Okay. Now, what's a buffer? Buffer in the English language is used to describe any number of things. In chemistry, an acid-base buffer has a very restricted definition. And all it means is that if your solution is buffered, then if you add a strong acid or a strong base to that solution, the pH is not going to change very much. It'll change a little bit, but not much. As opposed to what? If you put acid into pure water, that pH goes in a hurry. Or if you put a base, a strong base in water, it goes like that. pH goes up. But if you do that to a buffer, it may go like this or like that. And there's a chemical reason for that. Now, most buffers, not all, most are composed of a salt, of a weak acid, and a strong base. For instance, acetic acid. So if we have acetic acid, then the buffer will have some of this in it and some of that in it. Like that. The buffered solution will have some of that and some of this. And you decide how much. And how much determines exactly the characteristics of the buffer. So these two chemically active species in your buffer, this one or that one. One of them will react if you add a base. The other will react if you add an acid. Well, actually, yeah, okay, that works. So if you add hydroxyl ions, they react with the hydroniums. So in that case, I need to draw it this way. Water produces hydronium. That's chemically accurate. So if we add hydroxyls, the hydroxyls are going to react with hydronium. Right? They're not going to react with that one. We could also describe this in terms of the hydroxyls reacting with that, and it'd be the same result. But I'm trying to stay with the slide set that the authors produced. So what do you get when you react these two? Well, this one, remember, let's go back. Like that and like that. Right? And this is mostly over here, right? So water is extremely weak acid, which means that's a very strong base. I mean, massively strong base. So it's going to go for protons wherever it can find them. So if we add hydroxyls to the solution, it's going to get a proton from somewhere. And it's going to take it from the hydronium, which produces what? Well, actually two waters, right? Leaves this water behind and that water. Okay, if you remove that from this solution and it's in equilibrium, so I'm going to give you a taste of Le Chatelier's principle before we get to it. When you remove this one, the equilibrium will shift to the right to replace some of those hydroniums so that we get a balance again. So when it does that, what does it do? Well, it replaces some, but not all. That's why the pH will change a little bit. But it will replace most of these hydronium ions by ionizing that acid. Okay, and reacting with water. So that's how the pH is stabilized when you add a base to it. Now what happens when you add an acid? Well, let's see, let's get rid of it. Let's get rid of this scenario. Now what happens when you add an acid? Well, if this is a weak acid, these are both, well, this is a strong base. This is an acid, weak acid. This is a strong conjugate base. And it's just like hydroxyls in that respect. It's looking for protons. So if we add an acid, a strong acid, it's got those hydrogen ions, then this species here is going to pick up those protons readily and go back this direction. Right? So when it does that, and those protons are in the reaction, and it ends up over here, then we're going to have to reestablish equilibrium again. And in order to do that, this is going to dissociate to a certain amount and produce some of these. So that again produces these and that. So pH is expressed in this term. So by moving back this way, once these are removed, like we produce this acid, then part of it dissociates again to produce some of these hydroniums, and the pH is stabilized again. That's the chemical explanation for buffer activity with a weak acid and its strong conjugate base. So how do we get to this point right here? Well, there are two ways. You can either take this acid and titrate it, add strong base until you get to a certain buffer pH. Or you can just take the salt and put it in solution. Okay. And that's going to produce, well, initially, it's going to produce sodium ions and acetate ions, H3, like that. And then this is going to react with water molecules and produce some of that. So that's a direct route to producing a buffer. Because once you get this, it's going to react with water and produce some of these. Just depends on how much of this you put in solution. That's one way to do it. Or you take this, a certain amount of this, and a certain amount of acid, and put them together to begin with. And as it turns out, the best concentration of this one and that one is 1-to-1 molar ratio, with the same amount of the acid as you do the conjugate base. And you get a buffer, an ideal buffer, in the middle of its buffer range. All right. Let's see. All right. So once the, well, first, a researcher called, his name was Henderson. Can't remember his first name. Henderson was working with equilibrium, acid equilibrium solutions. And he wanted to know if we had an acid of any kind and we put it in solution, what pH can we, what hydrogen ion concentration can we expect? Henderson was working before Sorensen introduced the idea of pH. So Henderson was only privy to this expression. Right, the conjugate base and then the acid of that. So he wanted to know what's the hydrogen ion concentration. Well, he just solved the equation. Right? Hydrogen ion concentration equals, and then he put Ka and times Ha over A minus. I just solved it for hydrogen ions. Okay, so that was Henderson's contribution. Let's see, I think it goes here. There we go. Hasselbalch came along after Sorensen introduced the pH concept. So Hasselbalch took Henderson's expression, he took the negative log of the whole equation. So he took the negative log of this side, and he took the negative log of this side. And what he got over here was pH equals negative log of Ka, which was pKa. But he didn't want to break this one up, so he left it alone. And he said negative log of Ha over A minus. But he wasn't too fond of negative values in his equation. So he said, how do I get rid of that negative? Well, it's a identity of logarithms that if you have a quotient of two values, two variables in a logarithm, and you invert it, change the sign. So we just said, okay, I'm going to flip those, and that comes out to pH equals pKa plus the log of the conjugate base divided by the weak acid. That's the Henderson-Hasselbalch equation. And there we go. All right. One thing we notice is, you know the pKa of your weak acid. And if the ratio of conjugate base to acid is the same, in any solution you make, you're going to come out with the same pH. So if this is a very low concentration, you get a certain pH. If this is a high concentration, but they're exactly the same ratio, say it's 1:1, right? If it's 0.1 molar, 0.1 molar, or 1 molar, 1 molar, you're going to get the same pH for both of them. All right. So what's the pH of a buffer solution that's 0.45 molar acetic acid and 0.85 molar sodium acetate? All right. So in that case, the acetate ion is the conjugate base. So the concentration, since sodium acetate does this number, let's see, let's erase this and make room. So the conjugate base is going to be produced from the dissolution of this molecule, right? Sodium ions plus acetate ions. And that concentration is going to be the same since it's 1:1. This is going to be the same concentration as given. That's 0.85 molar, 0.85 molar. And the acid is 0.45 acetic acid. So that's this one right here, 0.45 molar, and this one is 0.85 molar. So we need to know what pKa is. Well, the Ka is 1.8 times 10 to the minus 5. Like 1.8 times 10 to the minus 5 is the pKa, the Ka. We need to know the negative log of that value to put it in our equation. Let's see, 1.8 exponent -5, take the log, change the sign, 4.74. There we go. Now we can calculate the pH. We just need 0.85 divided by 0.45, correct? Yeah. Divided by it, and then take the log of that and add it to this value. This is 0.276, and we add it to this one. And the pH, let's see, 2 decimal places, so I'm going to have to restrict it to 5.02. Should be the pH of that solution. And there we go. Okay. Henderson-Hasselbalch equation is extremely useful. We, in my general chemistry class, we calculate the pH of acid-base solutions or buffer solutions using what's called an ice table. Sometimes you have to use it, but if you can get equilibrium concentrations for your acid and conjugate base, this is a whole lot quicker. Less strenuous. Okay, so the conjugate base divided by the acid is that last term. All right, let's see. I'm almost out of time. Am I close to the end? Electrolytes. Let's see. Because I don't want to eat up your lab time. Electrolytes and then indicators. Okay. We might have to go over just a little bit. Electrolytes are operationally defined. An electrolyte is any compound in aqueous solution that will conduct electricity. What that means is they must dissociate into ions. Right? Because if you put two electrodes into a solution that's connected to a battery and a light, and you try to get a current through that solution, it's not going to go unless there's some charge that will carry the charge from one electrode to the other. That's why when you put two electrodes on a big cube of rock salt, sodium chloride, you get nothing. Those ions are locked in place. If you put that sodium chloride in solution, now the sodium ions and the chloride ions can move. Or you melt it, put your electrodes in melted sodium chloride, but that's kind of warm. You'll still get a circuit and the light bulb will come on. That's operationally defined. So anything that doesn't conduct electricity in solution is a non-electrolyte. For instance, table sugar, right? Sucrose. You put sucrose in solution and try to conduct electricity, nothing happens. Because the sucrose, while soluble in water, does not produce ions. It simply gets hydrated. Strong electrolytes are compounds that completely dissociate, like sodium chloride, like potassium chloride, like sodium nitrate. They completely dissociate in solution and will conduct electricity very efficiently. So your light bulb gives you a strong light. Weak electrolytes, on the other hand, only conduct weakly. Best example of that is either partially soluble salts, partially soluble bases like our calcium hydroxide, or weak acids like acetic acid. Will only conduct electricity very weakly. All right. This concept, it's only introduced because it may be useful, especially if you're going into a laboratory setting and you're going to be using acids and bases a lot, salt solutions a lot, and reactions involving them, is the concept of the equivalent. The equivalent references, well, let's restrict our definition to acids and bases. If you have, say, 1 mole of sulfuric acid reacting with something, say a base, reacting with some base, strong base, then if you have 1 mole of this, then how many moles of base, say the base is only monohydroxyl. Let's put something real in here like that, okay? It only produces 1 hydroxyl ion, but you've got 2 hydrogen ions over here. So for every 1 mole of sulfuric acid, it can neutralize 2 moles of sodium hydroxide, right? 1 hydrogen goes to 1 hydroxide, the other hydrogen goes to the other hydroxide. Remember, hydroxide is a very strong conjugate base. It'll strip off both hydrogens and produce 2 sodiums, 1 sulfate. This 1 molar sulfuric acid is the same as 1 normal, or it has, 2 normal, sorry. It produces 2 equivalents of hydrogen ions. Okay. So if you have an acid that is monoprotic and you have 1 mole of it, you also have 1 equivalent. If it's diprotic and you have 1 mole, you have 2 equivalents. For phosphoric acid, you have 3 moles of hydrogen in 1 mole of phosphoric acid. You have 3 equivalents. So what is it equivalent to? Right? It's equivalent to 1 base. Or actually, this would be equivalent to 2 bases. That's why it's 2 equivalents. The advantage to thinking in those terms is if you know how many equivalents of your acid you have, it doesn't matter what the acid is. It'll still react with 2 equivalents of base. And if you have 2 equivalents, say this is this is 1 mole, excuse me, and this is 2 mole of acid. If you put this in 1 liter of solution, so this would be one mole of sulfuric acid. In 1 liter is 1 molar, right? Okay. It dissociates in a reaction to 2 equivalents. So that's equal to 2 equivalents per liter, 2 equivalents of hydrogen ions per liter is equal to 2 normal. Instead of molar, we say normal, because now we've changed our numerator from moles to equivalents. And if you know the normality of your solutions, then it doesn't matter what the acid or base is. You can calculate the consequences, the reaction results. A milliequivalent is simply 1,000th of an equivalent. So if you have, let's see, major electrolytes in blood plasma. Yeah. Okay, so when your doctor gets the results back from the lab, they're going to be expressed in terms of equivalents. Milliequivalents of sodium in your blood are 138 per liter. That would be normal. Potassium would be 5, so there's a lot less potassium than there is sodium, calcium, magnesium. Your anions can also be expressed that way. Expressing them in terms of equivalence means that you can think in terms, not in terms of the charge on each of the ions or the electrolytes, but in terms of you're comparing apples and apples now. Whereas if you have to think of them in terms of this one's got 2 plus charges, this one's only got 1, then it gets confusing. And doctors can't afford to be confused. So we issue the values in terms of equivalence. All right. So let's see. Concentration of calcium ion present in the sample is 5.3 milliequivalents per liter. How many milligrams of calcium ion are present in 180 milliliters of the sample? All right, this is a dimensional analysis problem. So if you start off with 100 milliliters of sample, you want to know how many liters, because the conversion factor of 5.3 is milliequivalents per liter. So 180 milliliters is 0.18 liters times 5.3. That gives you the number of milliequivalents. Then you convert milliequivalents to equivalents. Okay? And how many moles of calcium ions per equivalent? Well, it's a half a mole of calcium, or for each mole of calcium ions, you have 2 equivalents. So that's that factor on the far right. Once you have the number of moles of calcium ions, then you can convert it to, using molar mass, you can convert it into moles. Grams, excuse me. We've already got moles. Convert it into grams, and then the question says how many milligrams. Then you need a conversion factor. Just change those grams back to milligrams. And like any chain conversion, You want to check to be sure that you've canceled all the right ones and you're left with the one you want. We're left with milligrams. So 19 milligrams of calcium ion is contained in this 180 milliliters of solution. That is 5.3 milliequivalents per liter. Let's see. Just while discussing the mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. The concentration of ions is specified using the equivalent. That way also, you can add multiple different types of ions based upon their equivalent concentration rather than having to express them separately. So when we are entering a titration where we have acid and base, a titration says we know the concentration of one of them. Say, let's fix it at, we know the concentration of acid. And if we express the concentration in terms of how did we get there? Right, so we have, let's say we have 0.2 molar acid. Let's say C2H3O2. So how do we calculate molarity? Molarity is moles of acid per liter. Right? Okay. So if we put a certain volume of acid in a beaker or an Erlenmeyer flask, then we know we can calculate how many moles we just put in there. Say we used, I don't know, 25 milliliters, which would be what? 0.025 liters. So the moles of acid would be this one times that one. So 0.2 times that, 2/10. So that would be 0.0050, right? Moles. Acetic acid. Okay. We know that's how many moles we have in this container. Right. Now we're going to add base. Okay. Until we have exactly the same amount. Then we have sodium hydroxide. Okay. So this acid concentration is the concentration of hydrogen ions. The moles of base will tell us how many hydroxyls we add. And since the stoichiometry is 1:1, then with this volume, we can calculate, let's say, molarity of the base equals moles of base per volume of base, or liters of base. So if we know we have this many moles in our container, and we add enough volume of base to equal that, then we know that this value here is also going to be 0.0050 moles, right? And we know the volume that we added. Say we added, I don't know, 10 mils. So how many liters is that? 0.010 liters. Okay. So divide that into it. Let's say, let's move it 2 places. 0.50 molar sodium hydroxide. That's a titration. We're using the stoichiometry of the reaction to determine the concentration of an unknown concentration against the known concentration of acid. And it's based upon that equation. We know the hydrogen ion concentration, but we don't know the hydroxyl ion concentration. Then we compare them once we reach equivalence point. In other words, neutrality. And there's the setup. That's a burette on the top. We just ran out of time in order to do one of these reactions. Now, you can do this reaction with a pH meter, and the pH will depend on the acid and the base that you're using, the pH at equivalence. Or you can use an indicator. If you know the pH at which equivalence is going to occur, then you can select an indicator that will change colors very close to that pH. And that's a whole lot more convenient than trying to measure the pH each time. Especially if you're going to do 100 titrations in a day. And I've done 100, 200 in a day. So using an indicator that'll change colors when you get to the equivalence point, and then you can do your calculations from there. The difference between the equivalence point, which is the actual pH at which equivalence occurs, and the color change, which is called the end point. You want your end point color change to be as close to the equivalence point as possible to minimize error. So here we add some acid or base out of our burette until the color changes. And then we measure how much did we add. So that's why burettes are measured from 0 at the top, in our case, 50 milliliters at the bottom. We want to know how much we delivered. So if we start at 0 and we go down to, say, 20, we delivered 20 milliliters. Okay, let's see. I'm going to have to breeze through some of these. All right, so if you have that molar concentration of hydronium ions, then that's going to be 7.03. All of them are that. So that's pretty close to neutral. Not exactly, but very close to neutral. And the hydroxide ion concentration is going to be just a little bit above 10 to the minus 7. Okay. I'm going to have to leave that until we do our review. So work on this type of problem in your review. Oh, I will say this. If you have a monoprotic acid and a monohydroxyl base, you can use this expression. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. If your acid is, say, diprotic and your base is monoprotic, then you can't use that. In this case, you would have to use the normality. You'd have to calculate the normality of the acid rather than its molarity. And in that case, this always works. The normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. That one always works. This one works if the acid and the base produce the same number of ions for a reaction. So a monoprotic and a monobasic acid together, or a diprotic and a dibasic together, then you can use this one. And the reason you can use that is because moles of acid have to equal to the moles of the base. And since molarity is equal to moles divided by volume, then moles equals molarity times volume. That's where that comes from. Moles equals moles. So that one equals that one. In this case, you'd have to use equivalence. And that's why normality is so useful, because then it doesn't matter what the acid and base are. All right. Let's see. Okay, we're done.